In this video, we're going to do some examples of using the method of substitution to compute indefinite integrals. In these examples, we're going to look at some functions which aren't obviously substitutions. So the first one is the integral of ln x quantity squared over x dx. This is a function that we don't know how to do yet. We don't know how to integrate. When you see an example like this, the first thing you should ask yourself is, do we already know how to do it? Is it something that has an elementary antiderivative? If not, the next thing you want to ask yourself is, can I use substitution? Out of the various techniques that we'll learn, substitution is often the easiest, although not always. In this particular case, it might not be completely apparent what the composition is, but we can see that there is a composition with an inside function, namely the natural logarithm inside the square function. And indeed, that is what we want to let be our u. U equals ln of x. Then du is the derivative, which is 1 over x, and then there's a dx. Now you can see the 1 over x hiding in the denominator here, because this is actually the same as the integral of ln of x quantity squared times 1 over x dx. So now we have ln of x quantity squared, that becomes u squared, and 1 over x dx, that's our du. So now we can integrate this, because this is now something that has an elementary antiderivative. It's just a power function. So this is u cubed over 3 plus a constant of integration. And of course, always at this point, you need to remember to plug back in your u equals some function of x, namely, in this case, ln of x. So that goes back into our u, and so we end up with the natural logarithm of x quantity cubed divided by 3 plus c. Now once again, a good way of checking to make sure that this is the correct answer is to differentiate it. If you differentiate it, you will indeed get ln of x quantity squared over x. It's not hard to check because we just have to use the chain rule. The derivative with respect to x of ln of x quantity cubed over 3, we don't need to worry about the plus c because the derivative of the constant is 0. So we use the chain rule, the 3 comes down, then we have ln of x quantity squared over 3, and then we multiply by the derivative of ln of x. The 3's cancel, and you end up with ln of x quantity squared divided by x, which is what we started with. So that's how we have some idea that it is the correct answer. Let's do a variant of this problem. The integral of, let me try that again, the integral of ln of x over x dx. This is essentially the same problem, but it's not obvious in this case that there is a substitution to be made because we don't see any composition here. There is nothing raised to the second power here, so it's not obvious that there's a composition. I suppose if you want, you can imagine thinking of this as ln of x to the 1 power. However, it's not immediately obvious that there's a composition here to choose a u to be anything. But indeed, just like in the last problem, you want u to be ln of x. du is then the derivative, which is 1 over x dx. After that, it happens pretty much the same as the previous problem. We rewrite this ln of x times 1 over x. And then this is the integral of u du, which is u squared over 2 plus a constant, where of course u is ln of x, so we have ln of x quantity squared over 2 plus a c. So it basically works the same way, but looking at this problem is good because this is a kind of problem where it's not immediately obvious that there's a substitution to be made. This doesn't seem to be a composition. In fact, it's a quotient. Now, there is no quotient rule for antiderivatives for indefinite integrals. So instead you have to look for something else, and in this case it's a substitution. Let's try another example. For this one, let's do something that, again, it doesn't immediately look like a substitution is the way to go. The integral of tangent of x dx. This one might be a little bit surprising because you think, well, we know how to differentiate the trig function, so surely we know how to antidifferentiate. But it turns out finding antiderivatives for things like tangent or some of the other trigonometric functions can be quite tricky. In this particular one, we don't actually know off the top of our heads some function that if you differentiate it you get tangent. So how do you proceed? Well, we're looking at examples of substitutions, but it certainly doesn't appear that there's a substitution here. This doesn't look like a composition in any way, shape, or form. But that's only because we've written it as tangent. At this point, we just want to remind ourselves that tangent has another definition. Namely, it's sine over cosine. And that's how we want to rewrite this. We want to write this as the indefinite integral of sine x over cosine of x dx. And now we have a composition. Namely, we're looking at cosine of x being inside the reciprocal function. Let me rewrite this just a little bit. This is the integral of 1 over cosine of x times sine of x dx. So this is now, we can see cosine in the denominator. So when we call it the inside function, it's inside the denominator, or the reciprocal function. So in this case, we're going to let u be equal to cosine of x, and then du is the derivative, which is the opposite of sine of x dx. Now here we have sine of x, but what we actually need is we need a minus sign. So let's just put a minus in front of that. Let me put some parentheses around it so that way we don't accidentally think that we're subtracting. We're multiplying by -1, but of course if you multiply by -1, you have to put a minus sign in front as well, because minus a minus is positive. But at this point, we now have 1 over cosine of x is 1 over u, and the opposite of sine of x dx, that's our du. So what do we have? We have that this integral is minus, or the opposite of, the indefinite integral of 1 over u du. And this is one that we know. This is an elementary antiderivative. This is minus ln of the absolute value of u plus a constant. And of course, what is u? U is cosine of x. So we can write this as minus ln of the absolute value of cosine of x plus a constant. That is, plus a constant. And that's our answer. And sure enough, if you compute the derivative of this, you do get tangent. However, there is another way that this is commonly written. So let me just write this as a remark. And let me remind you that minus ln of some expression, let's just call it t, is equal to ln of t to the minus 1. Well, in fact, if you have any p in front of this natural logarithm, that's the same as ln of t to the p. Here we're treating minus as minus 1. So we can actually use this on our antiderivative. Minus ln of the absolute value of cosine of x is equal to ln of absolute value of cosine of x to the minus 1. Now, you might remember that this is 1 over cosine of x. Well, there's some absolute values there. And 1 over cosine is another way of writing secant. So this is ln of the absolute value of secant of x. So it's very common to write the antiderivative of tangent this way. Let's write it out now. So the indefinite integral of tangent of x dx, well, it does equal minus ln of the absolute value of cosine of x, as we just saw, plus a constant. But it also equals ln of the absolute value of secant x. It's commonly written this way because then you get rid of the minus sign. So there we have the antiderivative tangent, and we found the antiderivative tangent by using a substitution. You can actually do something similar to find the antiderivative of secant. Let's write that down. This is example D. The antiderivative of secant of x dx. Now there's nothing special about x as my variable. We could be using any variable. It's just standard to use x when there's no other variable around. But we could be doing this with secant of theta, for example, or secant of s, or secant of t. Whatever variable you happen to be using, you can use the same techniques. Now, the antiderivative of secant of x is found using a technique which is similar to the one used for tangent, but much more bizarre. It's the type of problem that you probably wouldn't come up with on your own. It's highly unusual in the way that it's done. Because what we're going to do is we're going to write it as a fraction, but probably not in the way that you expect. So here's what we're going to do. I'm going to rewrite this as the integral of secant x, and now I'm going to multiply it by something. Now I'm going to multiply it by a fraction. I'm going to multiply it by a clever choice or an unusual choice of 1. That is to say that whatever ends up in the numerator is going to end up in the denominator as well. Well, there's no point in me keeping the secret from you. The thing that you're going to multiply it by is secant x plus tangent x in the numerator, and the same thing in the denominator. Now, we'll talk about why we're doing this in a second, but just first observe that I'm allowed to do this because I'm dividing by itself. I'm dividing secant plus tangent by secant plus tangent. So really, this is just 1. So I am allowed to multiply by this because I'm allowed to multiply by 1 without changing anything. Now, a better question is, why would we do something like this? Now, it's probably not immediately clear, but what we can do is we can just multiply that secant x into the numerator. So the first thing is that we're going to have secant x times secant x. So that's going to give us secant x quantity squared. Plus, and now I'm going to do secant x times tangent x, so that's going to give me secant x times tangent x. The denominator I'm not going to do anything to, except maybe I'll write it as tangent x plus secant x. All I've done here is I've just swapped the order. So instead of secant plus tangent, it's now tangent plus secant, but of course we can do that. Now, the better question is, why would we even think to do that? This is actually a case where we can use a substitution. And we're going to have the same kind of substitution that we did with tangent, where we let u be the denominator. U is going to be that denominator, tangent x plus secant x. Well, why would that be, you might ask? U equals tangent x plus secant x. Once you have that, the next thing to compute is du. Well, what's the derivative of tangent? The derivative of tangent is secant squared, which just happens to be in the numerator. Secant x squared. Plus the derivative of secant next. Well, the derivative of secant is secant times tangent. And of course, all of this times dx. So now we notice that this is exactly the numerator. And u is exactly the denominator. So what we end up with is we end up with the integral of 1 over u du, which of course is ln of the absolute value of u plus c. But now we just plug in u back into this natural logarithm right here. And what's that going to give us? That's going to give us the antiderivative of secant of x dx is equal to ln of the absolute value of tangent of x plus secant x plus our constant of integration. And that's the antiderivative of secant, which again we obtained using a substitution, and certainly not an obvious substitution. Let's do one more example. Example E. In this case, we're looking at the definite integral of x times the square root of 2x plus 1 dx. I'm not really happy with that radical symbol, so let's try it again. That's a little bit better. So here we have x times the radical 2x plus 1. So immediately you should notice that we do have a composition here. Namely, the 2x plus 1 is inside a radical. So that suggests that perhaps we should let u be equal to 2x plus 1. Okay, that seems okay so far. In that case, what is du? Du is the derivative, which is just 2, and then put a dx at the end. Now, there's no 2 here, but of course you're allowed to put in a 2. So this is the integral of x square root of 2x plus 1 times, and let's leave a little space here for a minute, dx, and now let's come back with a different color and put a 2 there. So now by putting that 2 in there, I've doubled everything, so it's twice what I want, so I better put a 1/2 in front. Okay, so what are we looking at now? Well, this 2dx is exactly our du, which is what we wanted, and now we have the square root of 2x plus 1, that's the square root of u. However, we got a bit of a problem. Namely, there's still an x there. What are we supposed to do with that thing? Well, what you can't do is just leave it as an x. If you're changing x's into u's, you have to change all of the x's to u's. You can't just leave it lying around as an x. So it might seem like this is going to be trouble, because what are we going to do with that x? Well, it turns out we've already got the tool that we need. We know that u equals 2x plus 1, so solve this for x. Solve that for x. So the first thing I do is I subtract 1. Now I divide everything by 2. And that is going to equal x. So anywhere that I see an x, I can just plug it in 1/2 u minus 1. So let's do that. Let's plug that in there and give that as 1/2 u minus 1. Okay, well let's give that a try and see what happens. So we have a 1/2 in front, that's this 1/2. And then we have an integral, and now there's another 1/2. So we have two 1/2s. 1/2 times u minus 1 times the square root of u times 2 dx. Well, good news. Well, I don't want 2 dx, sorry. I want to replace that with du. But anyway, still good news. You can take out that 1/2. So that's going to give you 1/4 times the integral of u minus 1 times the square root of u du. At this point, you might think that maybe we're no better off. We started off with x and then times something in a radical. Now we've got the same situation but with u's. But this is actually okay. We still have a u in a radical, but we can now just rewrite this u as u to the 1/2. So now we're going to have 1/4. Let me try that again. 1/4 times the integral of u minus 1 times u to the 1/2 du. And this makes everything better, because I can actually just multiply that u to the 1/2 times u minus 1 using distribution. So this is going to be u to the 3/2 minus u to the 1/2. All of that times du. And now suddenly I have two power functions. Well, the difference of two power functions. Now this u right here is starting to look like a 4, so let's just fix that u. So we have 1/4. Let's just rewrite it for fun. U to the 3/2 minus u to the 1/2 du. So this is going to be equal to 1/4, and now we just use the power rule, or the reverse power rule as you might like to call it. We add 1 to the exponent to get 5/2, and then divide by 5/2, minus u, add 1 to the exponent, you get 3/2, divide by that new exponent, which is 3/2, plus a constant. Now you can simplify this a little bit, because this is 1/4, and you can write this as 2/5 u to the 5/2 minus 2/3 u to the 3/2 plus c. This is kind of convenient because you've got a 2 there and a 2 there and a 4 there, so you can simplify it to 1/2 times 1/5 u to the 5/2 minus 1/3 u to the 3/2. And that's about as simple as you can make it, although you could also distribute that 2 in, so you'll have 1 over 10 u to the 5/2 minus 1 over 6 u to the 3/2 plus c. At some point, you might forget that this problem actually started life in terms of x's. We're in u's now, but you have to go back and remind yourself that u was equal to 2x plus 1. So let's write that down. U is equal to 2x plus 1. So what you want to do is you want to take that and plug that in everywhere you see a u. 1 over 10 times 2x plus 1 to the 5/2 minus 1 over 6 times 2x plus 1 to the 3/2 plus a constant. And there you have your antiderivative. There's actually another way to do this one, which is perhaps not an obvious way. Let's do this problem in a different way. So this is alternate method for this example. This is what we call a rationalizing substitution. And you use it when you have a square root, basically. So the integral in question was x times the square root of 2x plus 1. What really makes this problem difficult is the fact that you have this 2x plus 1 underneath a radical. It's difficult to work with radicals sometimes. So what you might want to do is you might want to try to substitute it away. So let's let u not be 2x plus 1, but let's let it be the square root of 2x plus 1. Now you have to be very careful when you're doing a substitution like this. The result will be that there won't be a square root. However, there's a price that you have to pay. Namely, computing the du is a little bit more complicated. Now there are a couple of different ways that you can do it. One is just to directly compute du by computing the derivative. So of course, let's rewrite this as 2x plus 1 to the 1/2. Now we have to use the chain rule. So we're going to have 1/2 2x plus 1 to the minus 1/2 dx. So there's not really a whole lot of hope of us spotting that over here. However, that's okay, because if I rewrite this just a little bit, this is 1/2 1 over the square root of 2x plus 1 dx. Notice that 2x plus 1 in a radical is exactly our choice for u. So we can rewrite this as du equals 1/2 times 1 over u dx. And I don't see any u's here, of course, but I do have a dx. And here I'm writing dx in terms of u's. Well, let's solve for that dx. Let's multiply by 2u. So you put the 2u over here, du, that's going to give us dx. And so now that gives me what I can substitute into there. So this is going to give me the integral of x times this expression, which is u, times this dx, which we now see is 2u du. So this is going to give me the integral of something which is equal to x times u times 2u du. Now, why did I leave such a big space there? I need to do what I did before, which is solve for x. We have u equals the square root of 2x plus 1. So we want to solve this for x. right? Because this thing right here, that's x. But we can't leave an x in this problem. We've got to turn everything into u. So solve this expression for x, which is a little bit more difficult than last time, but not a whole lot. You just square both sides, and then you get u squared equals 2x plus 1. And then subtract the 1, u squared minus 1 equals 2x, and now divide by 2. So 1 half u squared minus 1 is equal to x. So where we see that there's an x, we just replace it with that. 1 half u squared minus 1. Let's rewrite this. So it's the integral of 1 half u squared minus 1 times u times 2u du. Now, we've completely changed this problem, so there are no x's anymore. This expression right here, that was our x. I've included just a little bit too much in there. This expression right there, that's our x. The u was our square root of 2x plus 1, and all of that, 2u du, that's our dx. So this is kind of a mega substitution. There's a lot of substituting going on here. But now notice that there are no radicals. Everything is polynomial. So this is the integral. Well, first of all, that 2 cancels with that 2, so that's nice. And now we can just multiply u squared minus 1 by u times u du. Well, u times u, of course, is u squared. So if we distribute that, we're going to have u to the 4th minus u squared du. And again, we have the difference of power functions. So we just use the power rule, or again, the reverse power rule. So you increase the exponent by 1, and divide by that new exponent. Notice that we have a 5 here, which corresponds to that 5 there. And the next one is u cubed over 3 plus a constant. Now that 3, of course, corresponds to that 3. And the next step is just to plug in u is whatever function of x. So we remind ourselves that u is equal to the square root of 2x plus 1. So u is equal to the square root of 2x plus 1, which I'll write as to the 1/2 power. Then I just plug that back in, and I'm going to have 2x plus 1 to the 5/2 over 5 minus 2x plus 1 to the 3/2 over 3 plus a constant. Now at this point we become keenly aware of the fact that we're off by a factor of 2 because our previous answer was half of this. So we go back to our original substitution and we realize we made a slight mistake in computing our du. So notice that we have u is equal to 2x plus 1 to the 1/2, so the 1/2 comes down, and then you multiply by 2x plus 1 to the minus 1/2, but then I have to use the chain rule and multiply by 2. So there should be an extra factor of 2 there, which will cancel with this factor of 2, like that. So this 1/2 isn't actually there, nor is that 2 there. So this shouldn't be here. That shouldn't be here, but this 1/2 should stay. So we should have an extra 1/2 in all of these. Now this 1/2 corresponds exactly to this 1/2 right there. So that's where that 1/2 comes from. So let's just multiply everything by 1/2. Now notice I don't have to multiply the c by 1/2 because c is an arbitrary constant. So half of an arbitrary constant is still an arbitrary constant. But I do need to fix this one and that one. So those should be half of what they are, or the denominator should be twice. So that's going to be a 10, and that's going to be a 6. And now we see we have the same answer that we got last time. So that's a good indication that we've done it right. Make sure you have the right answer, is to compute the derivative of what you got and see if you end up with the thing that you started with. Now in this particular type of example, it might not be obvious that it works, but let me show you. What you want to do is compute the derivative with respect to x of this expression. So you have 2x plus 1 raised to the 5/2 over 10 minus 2x plus 1 to the 3/2 over 6. Again, we don't need to worry about the plus c because if you differentiate the constant, it goes away. So we have to use the chain rule here. So you're going to have, well, there's a 110 that goes out in front. Let's just do that. That's the denominator. And then we're going to multiply it by the exponent comes down times 2x plus 1 to the 3/2, lower the exponent by 1. And then, of course, you have to multiply by the derivative of the inside, which is 2. And then we're going to have the same thing here. So we have a 1/6 in front times 3/2 times 2x plus 1 to the 1/2. And then we're going to multiply again by the derivative, which is 2. So all of these 2's will cancel out, like so. Now what are we going to have? We have 5 over 10, which is 1/2, times 2x plus 1 to the 3/2, minus 3 over 6, 1/2, times 2x plus 1 to the 1/2. Now this doesn't look like what we started with. What we started with was x times the square root of 2x plus 1. So you might think that we've made some kind of mistake, but you can actually factor out this 2x plus 1 to the 1/2. So this is 1/2. Let me rewrite this. This is 2x plus 1 to the 1/2 times 2x plus 1. That's this thing right there, minus 1/2 times 2x plus 1 to the 1/2. So we have a 2x plus 1 to the 1/2 there, and also a 1/2 there and 1/2 there. So we can factor those out. So you're going to have 1/2 times 2x plus 1 to the 1/2, and we're factoring it out, so that's going to leave a 2x plus 1 here, minus, and you're factoring out the whole thing here, so that's just going to leave you with a 1. But this is 2x plus 1 minus 1, that's just 2x. So what do you have? Well, that 2 is going to cancel with that 2, and you're going to end up with 2x plus 1 to the 1/2 times x. Or, if you prefer, x times the square root of 2x plus 1. So, in fact, we do get the right thing, and so we did find the correct antiderivative.